Hello and welcome to my presentation. I am Fabian Lichtner, a first-year PhD student at the Universitat Politecnica de Catalunya, and I'm going to present to you our work related to information retrieval of data and knowledge from academic databases. How do you look for knowledge in your research? In this time and age, the internet is arguably the biggest and easiest to access source of information. However, the amount of information stored in it grows rapidly, and pinpointing the sources relevant to you becomes an increasingly difficult task. Finding information is still the most stated usage reason for the 4.7 billion internet users around the world. In the vast amount of sources, Scopus, Web of Knowledge, PubMed, and others emerged as reliable sources for peer-reviewed academic content, and the focus of the presented study lies on information retrieval from such abstract and citation databases. Searching those databases can be a tedious and time-consuming task, considering the rapid speed at which content is created and shared. Here you can see the amount of entries contained in the biggest databases. On the right-hand side, you see the normalized amounts of papers published on two different topics that seem to experience an exponential growth. But one of them is a very general topic, namely time, whose growth is more likely driven by the yearly overall growth in publications of 9%. In process systems engineering, data and knowledge are always needed, especially considering the trend of data-driven modeling. Mathematical models build the basis for most of the works a process engineer does. These consist of equation and data. The equations can stem from expert knowledge and literature, while data is usually derived from experiments or historically recorded data from operation. Often, these two ways of obtaining data are time and or cost-intensive. Luckily, data can also be found in literature, so it would be desirable for a process systems engineer to facilitate the search of data and also knowledge. The general problem statement that we target can be summarized in the following way. Given a research question, a set of relevant documents, and an academic citation and abstract database, find an extended corpus of documents relevant to the given research question. We depart from a special situation where a researcher has already identified or has been given an initial relevant corpus of documents that respond to the research question. In order to retrieve information from abstract and citation databases, we need to formulate search strings. Often, this search string construction step is performed in an unsystematic procedure. We propose a more systematic procedure that follows the assumption that the seed documents contain linguistically relevant information that can be used to find documents with similar relevant content. To that end, we first need to extract the relevant keywords from the documents. Then we apply some systematic string construction method to obtain a list of candidate documents. And finally, this list must be evaluated in order to find the truly relevant documents that extend the seed corpus. This methodology is modular in the sense that each subtask could be exchanged with different methods. In the following minutes, I will introduce you to the tools that we selected for each task. The term frequency, inverse document frequency, or short TF-IDF, is an established metric to determine the relevance of a document of a keyword to a document. It can be formally calculated as shown here, and in brief, it considers that words that appear often in few documents are considered relevant, while frequent words in all documents and non-frequent words are non-relevant. Calculating this value for every word in our documents allows us to construct a ranked list of keywords with associated relevance values. So for the first step, we have used the TF-IDF method. When constructing query strings in databases, you use operators to connect a set of keywords that describe your research interest. On this slide, we illustrate the most common of such operators. An example search string to inform yourself about the topic of this presentation could be the one shown here. But how would you construct such a string? This is a non-trivial question, and there are a few tools out there to help with this task. One feasible strategy to construct query strings would be a sequential approach to connect only the most relevant keywords with end connectors until the number of resulting candidate documents is low enough to be handled by a human. Another approach would be the construction of of strings using expert knowledge to reasonably combine keywords together with all available operators until the resulting candidate list has a reasonable length and the quality impression seems satisfactory. A systematic approach based on such ranked keyword lists has been demonstrated by Marcos Pablos and co-workers in 2018. Finally, we propose a query construction strategy based on Monte Carlo sampling. The idea is to repeatedly sample keywords with the probability of inclusion in the string equals their relevance. Keywords are aggregated using AND connectors until the number of returned documents reaches a threshold. The appearance of individual documents is registered and counted. By repeating this procedure, we obtain an appearance distribution of individual documents. The more often a document appears, the more relevant it is to the seed documents that the keywords have been extracted from. The main advantage of this approach is that no trial and error procedure is necessary, and human expert knowledge and the possible bias introduced by it is avoided. So, for the search string construction, we have used and compared the three presented strategies. The results of the three strategies are different in the sense that the Monte Carlo method directly yields a ranked list of candidate documents thanks to the appearance frequency. The sequential and expert lists could be ranked through other metadata, such as number of citations, publication date, or others. But in order to compare the resulting candidates on a linguistic level, we employ a metric that is called Best Match 25, or short BM25. It quantifies the relevance of a document to a search string in relation to the whole set of documents. It can be formally defined as shown here, and the process is visualized here. So to evaluate the linguistic relevance of our documents, we use the BM25 metric. The case study that I'm presenting to you is related to another line of research that my colleagues present in this Congress, which is the identification and prioritization of waste-to-resource routes, more specifically the conversion of plastic waste to a raw material via pyrolysis. This approach foresees an ontological database containing data such as input plastic type and the products obtained at certain conditions such as temperature, pressure, the catalyst used, etc. Such data could be obtained through simulation and experimentation, but due to the increasing availability of data contained in scientific publications, we are targeting this information with our information retrieval methodology. As an input, we can state the research question, that is, the target of obtaining more entries to the ontological database. We depart from a seed corpus of 8 relevant papers that has been identified through a manual search and apply the procedure to the Scopus database. Here you see the titles of the documents that have been used to extract the relevant keywords. It turns out that obvious words such as waste, pyrolysis, product, etc. appear at the top of the list, and now we have a quantification of their relevance. We use these weights in the Monte Carlo sampling to determine the probability of each word to appear in the query. It is interesting to note, for example, the high position of WT, which is an indicator for a quantitative value of a composition that we are really interested in. Here you can see the search strings resulting from the sequential method, 3 strings composed by experts, and the Monte Carlo method has been applied with 1,000 iterations, meaning 1,000 different search strings. This is the distribution of document appearances in those iterations, and we can see that the top document appeared almost in every second search. These are the length of the resulting lists, and the Monte Carlo method yields a list with 116,000 entries. As I mentioned before, the sequential and expert results could be screened in order of some metadata like citations or publication date, and the Monte Carlo method yields a pre-ranked list that can be screened in order of appearance. Before using the BM25 to compare those lists on a linguistic level, I would like to briefly mention the capability of the method to re-retrieve the documents that have been used as seeds. The sequential method yields only 2 out of the 8 documents used in the candidate list, while the expert strings have 4, 5, and 6 respectively. The Monte Carlo method is able to re-retrieve all of the seed documents, with the top 7 of them being in rather high positions up to 500, and the 8th document is found in rank 2634. The fact that the method re-retrieves the documents used as seeds is a good indication that it really does what we want it to do. Next, we went ahead and downloaded as many of the candidate documents as we could for the sake of comparing the linguistic relevance of the full texts. In the case of the Monte Carlo list, we stopped at the document in position 2000. The complete set of documents has then been compiled and analyzed using the BM25 method. It is important to note that this task of downloading so many documents is not necessary when applying the method. Here, we simply do it to compare the performance of the different lists. The results are visualized here, where the retrieved documents in each list are ordered by the calculated BM25 value. We can see that there is a small amount of linguistically very relevant papers that have been identified by all methods. So, in order to find new relevant documents, all methods are applicable. However, the amount of retrieved linguistically relevant documents is clearly higher in the case of the Monte Carlo method. The main contribution of this work is the inclusion of Monte Carlo sampling in combination with TF-IDF relevance during the query construction step. This led to 2 desirable outcomes. First, human expert intervention, an expensive and scarce resource, is decreased, and second, potential human bias is avoided. In the performed case study from the chemical engineering field, the methodology yields promising results compared to the sequential string construction and strings composed by experts. The field of systematic literature reviews will benefit most from the method, but really any research that starts with a literature review will find it helpful. There are limitations to the methodology. One of them is imposed by the database. For example, Elsevier limits the amounts of queries made to their database to 20,000 per week. Another issue is that the sampling procedure itself can be time-consuming, and in its current implementation, it takes about 2 hours to perform 1,000 iterations. So it's not like a simple Google search or Scopus search that yields the results in a matter of milliseconds, but the results need to be generated through repeated retrieval and analysis of thousands of abstracts through the API of Elsevier. Future work will extend the comparison to other query construction methods to establish a benchmark for document retrieval performance from academic abstract and citation databases. Also, we are working on developing guidelines for the application of the method. If you're interested in applying it to your research, please visit the following website to submit some of your abstracts or papers that you want to find relevant documents to. Thank you very much for attending this presentation, and I will be happy to answer any of your questions.